Good evening. It is 6 p.m., but participants are yet to join, so we will wait for a couple of more minutes before we get started. Thank you. Good evening and welcome to week 5 of the live sessions for computational science and engineering. I am Sourav Goswami, a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. This course is taught by Professor Ashok Dey from the Department of Aerospace Engineering at IIT Kanpur. This week, we'll be talking about partial differential equations. Uh, Perhaps more importantly, we'll be building up to partial differential equations because, as you might have seen in the lectures, often based on the type of boundary conditions available, and of course, before that, based on identifying the type of equation that we're dealing with, we have to determine the eigenvalues of the problem and find the corresponding eigenvectors, which serve as the fundamental building blocks for the solution of such partial differential equations. So first, we'll try to build some intuition and some idea as to how to find those eigenfunctions and eigenvalues and eigenfunctions. That actually stems from a class of problems called the Sturm-Liouville problems. So here's the definition. The way you do it is you start with a special form of a differential equation, manipulate it to obtain the Sturm-Liouville, a standard Sturm-Liouville form. So given an equation of this sort, which is y double prime plus rx of y prime, rx y prime plus y times qx plus lambda px equals 0 on some open or closed interval a comma b. Lambda is a constant which is to be determined, and an inherent assumption is that the coefficient functions are continuous on the interval. After certain manipulations, the form we end up with is this, which is ry prime whole prime, or say ddx of ry prime plus q plus lambda p times y equals 0. And under the circumstances that P, Q, R, and R prime are continuous on A, comma B, and Rx is greater than 0, Px is greater than 0 on A and B, we call this equation the Sturm-Liouville differential equation. Now you would notice that it contains this quantity lambda, and based on the different cases which might arise or the different types of values which lambda might assume, the solution will differ. And these values of lambda are actually called the eigenvalues. And the key idea here is to solve these equations such that the solution is not trivial. Say the solution is not identically zero for the given set of conditions. We want to find non-trivial solutions. So we take cases on lambda and try to arrive at those solutions. Lambda are the eigenvalues, and they are chosen such that there are non-trivial solutions y of the differential equation which satisfy the given boundary conditions at A and B. And for each given or each determined eigenvalue, such a solution is called an eigenfunction associated with lambda. The conditions that must be satisfied on A and B are boundary conditions. We are well aware of that. And the Sturm-Liouville problem can be classified into three types. So first is the regular Sturm-Liouville problem, where the boundary conditions are regular, such as a1y of a plus a2y prime of a equals 0 and b1y of b plus b2y prime of b is 0. Even and a2 are given numbers, not both 0, and b1, b2 are given numbers also, not both simultaneously 0. The periodic form of the Sturm-Liouville problem is that the condition at one boundary A is same as the condition on the other boundary B, and we want numbers lambda for which there are non-trivial solutions of the equation. Ya equals yb and y prime a equals y prime b. So both the value of the function as well as the slope of the function is periodic, as in it repeats over the interval which is given to us. The singular Sturm-Liouville problem, where R of A is 0 or R of B is 0, but not both. And in this case, we want lambda, our eigenvalues, for which there are non-trivial solutions of the equation to satisfy the given boundary conditions. If R is 0, then there is only one single boundary condition, only one boundary condition, which is b1 y of b plus b2 y prime of b is 0, such that b1 and b2 are not simultaneously 0 because in this case we'll only end up with a trivial solution which is identically 0. If R at b is 0, then the only boundary condition available to us is a1 y at a plus a2 y prime at a is 0, where a1 and a2 cannot be both simultaneously 0. We'll solve a couple of Sturm-Liouville problems. We'll also solve a couple of PDEs. And the idea here is to change the types of boundary conditions given to us and then adapt our solution to those boundary conditions. This will allow us to cover a vast host of problems. So first, a couple of Sturm-Liouville problems to build up the idea and the intuition for getting the eigenvalues and the eigenfunctions. So this is an equation given to us. Let us compare it with the standard form of the Sturm-Liouville equation or the Sturm-Liouville problem. So the standard form as we discussed is edx rx times y prime plus qx plus lambda px times y is 0 subject to the boundary conditions a1 ya plus b1 y prime a is 0. So this is the regular custom level problem which we are talking about here, and a2 y at b plus b2 y prime at b is 0. So this problem is defined on, say, the closed interval a comma b. A and b mark the two limits or the two limits of the interval over which this problem is defined. And by comparing with the standard form, we can find that in the given case, Rx is equal to 1, Qx is equal to 0, Px is equal to 1 again, y of 0 is 0. So A1 is 1. We can write it as say, A1 y of 0 plus B1 y prime of 0 is 0. A2 y of L plus B2 y prime of L is 0. The conditions given to us are y of 0 is 0. So A1 is equal to 1, B1 is equal to 0 because no condition of slope is given to us. Similarly, from the second one, we can deduce that again A2 is equal to 1 and B2 is equal to 0 because the condition on the slope is absent. Of course, as usual, we start by assuming the solution of exponential form. So something like e power mx. Usual route, we substitute it into the given differential equation, see how things evolve. So this will turn out to be m square e power mx plus lambda e power mx is 0, which implies that m square plus lambda is 0. Now, as we were talking, now we'll take different cases on lambda and see how, based on the sign of lambda, so whether it is 0, positive, or negative, how the solutions evolve. So first, the simplest case. Let lambda equal 0. So in this case, m square plus lambda is 0 and will imply that m square itself is 0. So, or in fact, we can even put it into the equation directly. So y double prime itself is 0 because lambda is 0, which will imply that y prime is some constant, say c1, and y itself is some function which is linear, so c1x plus c2. Now, if we use the boundary conditions that y at 0 is 0, this will give us 0 equals c1 0 plus c2, or c2 is 0. If we use the other boundary condition y at L is 0 as well, we'll have 0 equals c1 times L. c2 has already been found to be 0, and since L not equal to 0, c1 must be 0. So we obtain the solution y is 0 because both c1 and c2 are 0, which is trivial. I mean, it is a solution, but it is more like a degenerate solution. It is not really helpful, does not give us any additional information which we might need to solve the system. For the second case, let us assume that. So we have an equation of the form m square plus lambda is 0. Let's assume that lambda is less than 0. And you will find that even when we are solving PDEs, we have to take these different cases on the eigenvalues, because only on the choice of the eigenvalue will the solution depend. And in most cases, even say a positive or a zero choice of the eigenvalue might not yield any solution at all, or at least a non-trivial solution at all. So this exercise becomes important. The more we often we do it, the more conversant we become. So for this case, we had m square minus lambda equals 0, or m square equals lambda. So we're dealing with squares. Something we can do is we can assume, say, lambda equals less than 0, so minus alpha square, where alpha square is positive. And the reason for this is alpha square will always be positive, so lambda will always be negative in this case, and alpha will, assuming it's not 0. So we'll always have lambda less than 0. So this is equal to minus alpha square, or which will imply that m is equal to plus minus. Did I do something wrong here? Oh, I have plus. That's what. Sorry. The equation we set out to solve is that m square plus lambda is 0. So m square is equal to minus lambda. Minus lambda is equal to plus lambda square, or m is equal to plus minus lambda. Now, from our sessions on ordinary differential equations, we already know that for the auxiliary equation which has solutions of this type, where m is equal to plus minus lambda, the standard solution will be equals c1 cos hyperbolic alpha x plus c2 sin hyperbolic alpha x. And we can arrive at a cos hyperbolic and sin hyperbolic functions by careful manipulation of the exponentials. Now, let us apply the boundary conditions to this case as well. So the first boundary condition is that y at 0 is 0. So 0 equals c1 cos hyperbolic 0 plus c2 sin hyperbolic of 0. We know that cos hyperbolic of 0 is 1. So, and sin hyperbolic of 0 is 0. This implies that c1 is equal to 0. Now for the other boundary condition, y at L is equal to 0. So 0 equals, we have c1 0 already. So c2 sin hyperbolic of alpha L. Now, if we remember correctly, the sin hyperbolic of x is equal to 0 only when x equals 0. So this can either mean that C2 is 0 or alpha L is equal to 0. But then L is not equal to 0. We have also chosen alpha not equal to 0, so C2 must be 0. Therefore, again, y is equal to 0, which is again a trivial solution because both C1 and C2 come out to be 0. Now, all our hope rests on the third case where we choose lambda greater than 0. Our equation is m square plus lambda equals 0. So we can imply that m square equals minus lambda. Since again we are dealing with squares, we can assume that lambda is some quantity alpha square, which will always be 0, greater than 0, always positive. So m square will always be negative minus alpha square, or m will be equal to plus minus iota times alpha. Again, from our discussions on ordinary differential equations, we know that for auxiliary equations of this type, the standard solution is C1 cos alpha x plus C2 sin alpha x. Now to find C1 and C2, we'll again apply the boundary conditions given to us. Y at 0 is 0. This will imply that 0 is equal to C1 cos 0 plus C2 sin 0. The second term goes to 0, cos 0 is 1, so C1 must be equal to 0. From the other boundary condition, y at L equals 0, we have 0 is equal to C2 sin alpha L. Now, here we are presented with two options. So, either C2 can equal 0, in which case we end up with a trivial solution because both C1 and C2 are 0, y is identically 0. Or the other possibility, which is perhaps more enticing, is that sine of alpha L is equal to 0. And we know that this equation has solutions of the form alpha L is equal to n pi. So whenever, so sine n pi is always 0 for all, say n equals 1, 2, 3, and so on. Why are we not taking n equal to 0, even though sine of 0 is 0? The only reason is that we want to use n as, say, some sort of index where we'll have, say, not one, but many eigenvalues, depending on the value of n. N is a multiplier here, and corresponding to each of these eigenvalues, we'll have corresponding eigenfunctions. So we just want to use n as an index here. So we start from 1, and if alpha n is equal to n pi, then alpha is equal to n pi by L, or lambda, which was equal to alpha square, is equal to n square pi square by L square. Now let us add the subscript n here to correspond to the n, and these values of lambda which satisfy this equation are the eigenvalues. Now corresponding to each of these eigenvalues, we have eigenfunction y of n, which was equal to C2 sine alpha n pi by x. And just by convention, we choose C2 equals to 1. So the solution is simply yn is equal to sine n pi by l x. Based on the value of n, which is a whole number, we'll end up with different eigenvalues and different corresponding eigenvectors. In this case, we had boundary conditions at or the values of the functions at the two ends. Let us also look at an example where we are given not the values per se, but the slopes of the functions at the two ends. So we'll proceed in a similar fashion by identifying first the various coefficients by comparison with the standard form. To y plus b2 y prime at b is 0. Now comparing the standard form gives us r of x is equal to 1, q of x is 0, p of x is 1, and for the given boundary conditions, they are defined only at the slopes. So a1 is 0, b1 is 1, a2 is 0, and b2 is 1. Again, we start by assuming a solution of the exponential form. So let y equal e power mx. And with this substitution, we'll again have m square e power mx plus lambda e power mx is equal to 0, which implies that m square plus lambda equals 0 is the characteristic equation. Now, we again take cases on lambda and see how things are different in this case where the slopes at the boundaries are given rather than the function values. So case 1 where lambda equals 0. If lambda equals 0, then again we simply put it back into our original equation. Y double prime is 0, which implies that y prime is some constant and y is a linear function in x. Now, if y prime at 0 is 0, y prime always is a constant irrespective of the value of x. So we have 0 is equal to c1. This is always true. Now y prime at L is 0 implies again that 0 is equal to y prime at is a constant, so irrespective of whether it is 0 at or L. So this will give us what? This has to be equal to 0 identically. So again we end up with y equal to 0, which is but a trivial solution and of little use to us. Now for the second case, we assume the eigenvalue to be less than 0, and our characteristic equation was m square plus lambda is 0, which implies that m square equals minus lambda. Now again, since we will have to take the square root, we'll assume lambda equal to say minus alpha square, where alpha square will be always positive, so that lambda is less than 0. So m square is equal to alpha square, or m is equal to plus minus alpha. Again, the standard solution in this case will be C1 cos hyperbolic alpha x plus C2 sin hyperbolic alpha x. Now we have the boundary conditions given to us for the values of the slopes. So it will be helpful if I just find the derivative. This one turns out to be alpha. For cos it is negative sign, but cos hyperbolic it is simply sin hyperbolic alpha x plus C2 alpha sin hyperbolic cos hyperbolic alpha x. Now let us substitute the values. So y prime at 0 is 0. So C1 alpha sin hyperbolic 0 plus C2 alpha cos hyperbolic of 0. Now sin hyperbolic of 0 is 0, cos hyperbolic of 0 is 1. So we only have C2 alpha, which will imply that C2 is equal to 0. Since alpha is not 0, we have explicitly chosen alpha square to be greater than 0. Again, y prime at L is equal to 0, which implies that C1 alpha sin hyperbolic of alpha L is 0. But we know that sin hyperbolic of any function of x is 0 if and only if x is equal to 0. So either sin hyperbolic of alpha L is 0 or C1 is 0. Alpha is not 0 because that is how we have chosen it to be. This is not true. Thus C1 must be equal to 0. And again, we end up with a trivial solution y equal to 0. We look at the third case where we assume the eigenvalue to be greater than 0. In this case, again, we assume it to be some alpha square where alpha square is greater than 0, and m square plus lambda is 0. So m square is minus lambda, which is equal to minus alpha square, or m is plus minus I alpha. So in this case, the solution takes the standard form C1 cos alpha x plus C2 sin alpha x. The derivative will be C1 minus C1 alpha sin alpha x plus C2 alpha cos alpha x. Now let us apply the boundary conditions given to us. Y prime at 0 is 0. So this is minus C1 alpha sin of 0 plus C2 alpha cos of 0 is 1 is 0. So C2 should be equal to 0 since alpha is not 0. Y prime at L is again equal to 0. So minus C1 alpha sine of alpha L is equal to 0. Now here we have two interesting possibilities. Either C1 is equal to 0 or sine of alpha L is equal to 0. If C1 is equal to 0, which might as well be true, we can only obtain trivial solutions of the form y is equal to 0. But if on the other case, we assume that sine of alpha L is equal to 0, then alpha L will equal n pi, as we saw with the previous problem as well, because the value of the sine function at all whole multiples of pi is 0. And again, this will imply that alpha is equal to n pi by L, or lambda, which is equal to alpha square, will equal n square pi square by L square. Now, to use again n as an index, we write lambda n. So lambda n is equal to n square pi square by L square. These are the eigenvalues of this given Sturm-Liouville problem. The corresponding eigenfunction y equals c2 is 0, so c1 cos alpha x, yn equals c1 cos alpha x n pi by L. And it is the convention to assume c1 equals 1. So we have as the eigenfunctions. Now again, since here we have a cosine function on the right hand side, unlike the sine function which would have gone to 0 for n equal to 0, we can also have the additional solution y when n is equal to 0 is cos of 0 is 1, which is a non-trivial solution. So we can also admit the additional eigenvalue lambda naught is equal to 0 for n equal to 0, and the corresponding eigenfunction y equals 1. Now, because we saw how to calculate the eigenvalues and the eigenfunctions by taking different cases on the parameter lambda. Now, when we encounter such situations again in PDs, we'll not do these detailed calculations. We'll simply examine the cases and know which one to choose, and then proceed to find the eigenvalues and the eigenfunctions. One class of partial differential equations which were discussed in class are the potential equation or the Laplace equation, which are defined thus: in two dimensionals, it's del 2u del x2 plus del 2u del y2 is 0. In three dimensions, the equivalent form is del 2u del x2 plus del 2u del y2 plus del 2u del z2 is 0. And where we have encountered the Laplace equation, at least off the top of my head, which I can think is, this represents the steady state heat conduction, where say the transient term del U del T is equal to 0. The another aspect which was touched in class is what is known as the Dirichlet problem of the Laplace equation, and it is defined thus. So any function satisfying Laplace equation in a region of the plane or in a volume of 3 space is said to be harmonic on that region, and a Dirichlet problem for a region D consists of finding a function that is harmonic and assumes specified values on the boundaries of D. Of course, these correspond to the boundary conditions which will be supplied to us, and these boundary conditions themselves are derived from the actual physical formulation of the system under observation. So, say based on the temperatures at each end or the gradients of temperature at the end, uh, the boundary conditions are formulated, and we will primarily be concerned with Dirichlet problems in the plane for the case of this class, in which D is a region that is bounded by one or more piecewise smooth curves. The Dirichlet problem for D is then to solve del square du is 0 on D, and u at any xy is f of xy for x and y in the domain D, where the function will be given to us. It will again emerge from the physics of the given situation, and the function f is formally called the boundary data for D. Now, some form of the Laplace equation was also solved during the lecture. We'll solve another form which has, say, a different function at one of the edges. So this is the question given to us. Solve the Laplace equation for a rectangular region D and the given boundary conditions. It's also graphed here for easier visualization. So at u of 0 comma y, the function value is 0 for all y lying between 0 and k. So when we move along this, when x coordinate is 0 and for all values of y, the value of the function u is 0. Similarly, when x is fixed at L and we move along y for the region y lying between 0 and k, the value of the function u is 0 again. Similarly, for y equal to 0 and we move along x, the between x equal to 0 and L, the value of the function is 0. And for y equals k, when we move along x between the region x equals 0 and L, the value of the function u is equal to fx. Fx is defined here. So this is just a generic, and fx is defined as x equals fx is x times pi minus x. Also, the dimensions are given to be equal to pi. An important note is that the Laplace equation can be solved by separation of variables, which was demonstrated in class, only if the boundary data is non-zero on only one side of D. So, like in this case, the region D had four sides. On three sides, the boundary data was given to be zero, but on one side it was non-zero, and it is only in such cases that the problem can be solved by regular separation of variables. What happens if the boundary data is non-zero on, say, multiple sides, not just one? That is something we'll examine in a subsequent example. So let's get started. The equation is del to u del x2 plus del to u del y2 is 0. Now, we try to solve it by separation of variables, and we already know that it can be solved because the boundary data is a non-zero on only one side, other three are zero, and that would imply that the function u, which actually depends on both x and y, can actually be, say, decomposed into some function of x times some function of y, and basically the variables can be separated. Now let us apply the boundary conditions available to us. So I'll just write them here. U of 0 comma y is 0, u of l comma y is 0, u of x comma 0 is 0, and u of x comma k is y minus x. Of course, we know that x goes from 0 to l and y goes from 0 to k. So u of 0 comma y is 0 will imply that x 0 times y of y is 0, which implies that, say, either x of 0 is 0 or y at all y is 0. If the second case happens to be true, if y of y is y at all y is identically 0, we'll only end up with the trivial solution. U of xy itself is 0. So we discard this and we assume this to be correct. So x of 0 is 0. Similarly, we have u at l comma y is 0, which implies that x at l times y for any given y is 0, which again presents the possibilities that xl is 0 since y cannot be 0 throughout. The third condition given to us is u at x comma 0 is 0, which implies that x at x times y at 0 is 0, which will imply that y at 0 should be 0 since x cannot be generally 0, or I mean it can be, but the solutions will end up will be trivial. And the fourth condition given to us is u at x comma k, k being pi here. So u at x comma pi is equal to pi times x minus x times pi minus x. X comma x, uh, x of x and y of y is equal to x times pi minus x. So yeah, we leave it as that for now. Maybe it will help us later. And the original form of the equation is del 2u del x2 plus del 2u del y2 is 0. Let us substitute our formulation that u of xy is variable separable. So some x of x times some y of y. So this will imply that what del 2u x. So this is x double prime y plus x y double prime is 0, or if we now divide throughout by xy, what will end up with is double prime by x plus y double prime by y is equal to 0, or x double prime by x equals minus y double prime by y equals minus lambda, where this lambda is equal to separation constant. The choice of taking minus lambda on the RHS rather than say only lambda is again by convention, and that is because it makes the following calculations relatively easier. We also see how that works. So with this assumption that double prime by x is equal to minus y double prime by y equals minus lambda, we proceed for the first case. X double prime, we have two equations here, so x double prime by x equals minus lambda implies x double prime equals minus lambda x, implies that x double prime plus lambda x equal to 0. And for x alone, we already found the boundary conditions. X at 0 is 0 and x at L is 0. Let us write those as well here. X at 0 is 0, x at L is 0. Now, remember the Sturm Liouville problem that we discussed some time ago? This statement or this problem also looks quite similar. In fact, it is of the form of the Sturm Liouville problem. So we already know how to solve it. The solutions in this case will constitute of the eigenvalues, which are lambda equals n square pi square by L square, and the corresponding eigenfunctions will be xn equals, maybe I won't have space, the corresponding eigenfunctions xn shall equal sine n pi by L x, as we just saw. Again, let us solve for y. So y double prime by y is equal to lambda, or y double prime equals lambda y, or y double prime minus lambda y is equal to 0. Now, the boundary conditions for y are y at 0 is 0. Only one boundary condition. The second one has a con is will be used later. You can just write it here nonetheless. Okay, no, it's not for y alone. It also has an x component. So y at 0 is 0. And this will have the solution. Again, going back to the Sturm Liouville problem we just solved, y is equal to d1 cos hyperbolic n pi by L. The separation constant or eigenvalue of the problem remains the same. So n pi by L y plus d2 times sine hyperbolic of n pi by L y. The constants d1 and d2 remain to be determined, and we can use the available boundary condition to do so. So y at 0 is 0 will imply that 0 is equal to d1 cos hyperbolic 0 plus d2 sine hyperbolic 0, which will imply that the other term is identically 0, cos hyperbolic is 1, so d1 is equal to 0. Therefore, the function y is of the form d2 sine hyperbolic n pi by L y. Again, by convention, we assume d2 equals 1 to give it the elegant form y equals sine hyperbolic n pi by L times y. In this case, the fundamental solution is equal to, for each corresponding index n, xn, yn, because that is the form we assume that it is variable separable, and the function u of xy is equals just the product of some function x and some function y. Thus, corresponding to each index n, we'll have a fundamental solution. Un is equal to xn yn. Xn was sin n pi by lx, and yn is sin hyperbolic n pi by ly. Now, as was discussed in the lectures, the solution to the overall Laplace problem is actually the series which will consist of these fundamental solutions. So the general solution to the Laplace problem is actually the series which goes from n equals 1 till infinity, and it will equal bn sine n pi by l x sine hyperbolic n pi by l y. Now to this general solution, we can apply the data, boundary data, which is u at x equals k is equal to fx, which is equal to x times pi minus x. So let us do that. X times pi minus x equal to summation n equals 1 to infinity pn sine n pi by lx sine hyperbolic. Now see that for value y, you already have the value of pi. So n pi by l times pi. Of course, L is also equal to pi for this particular question. Pn sine nx sine hyperbolic n pi square. Sorry, sine n pi, because ln pi gets cancelled out. And from the discussion in class regarding the Fourier series and the Fourier series expansions, we can see that this is in fact the Fourier sine series expansion of the function on the left hand side. So x pi minus x, where the coefficient is taken to be bn sine hyperbolic n pi. So it's as if I'm trying to expand or express this function as this infinite Fourier sine series. And once that is clear to us, we already know how to find the coefficients. So formula for the coefficient of the Fourier sine series will yield the following results. So this coefficient Bn sine hyperbolic n pi equal to 2 by L. So 2 by L integral 0 to L fx sine n pi by Lx dx. This is the formula. And here, as I mentioned, L is pi. Yeah. So Bn sine hyperbolic n pi is equal to 2 by pi integral 0 to pi. Fx is x times pi minus x sine of n x dx. Bn sine hyperbolic n pi 2 by pi integral 0 to pi pi x sine nx dx minus x square sine nx dx. And let us solve these integrals separately. So minus 2 by pi I1 minus say I2. Now both involve integration by parts. So let's do that. We also did a lot of it in the past week. So I1 is 0 to pi x sine nx dx. If we choose u equals x and v equals sine nx, then what we end up with is u into integral of v dx. So x into cos nx by minus n, and this will be evaluated from 0 to pi minus integral of differential of u, which is just 1 into integral of v dx. So again cos nx by minus n whole dx is equals pi times. Now for the first term, when we put x equals 0, the whole term goes to 0. So we have pi cos n pi by minus n, and the integral of cos nx is sin nx by n. We already have a negative sign, so plus sin nx by n square evaluated between 0 and pi. This comes out to be pi times pi. Now an interesting property here is that cos of n pi is equal to minus 1 power n. So this will simply be minus 1 power n. We also have a negative sign at the bottom. So maybe add plus 1 here by n. Sine of n pi is 0, sine of 0 is identically 0, so the second term goes to 0. So this is simply pi square minus 1 power n plus 1 by n. Did I run out of space? Okay, so let's just continue at the very end. So let us choose. Let us now solve the other integral. So I2 I2 was x square sin nx dx. Integral 0 to pi x square sin nx dx. Again, we assume our function u to be x square and v to be sin of nx. So I2 will turn out to be u into integral of v dx. So cos nx by n minus integral of differential of u into integral of v dx whole dx. Now this comes out to be only the first term, the second will go to 0. So minus pi square by n cos n pi plus 2 by n integral 0 to pi x cos nx dx. And we are iterating here. We turn up with another integral of the form u and v. So this will be minus pi square by n cos of n pi is minus 1 power n plus 2 by n. Now u into integral of v dx. So simply x into sin nx by n evaluated between 0 and pi minus integral of differential of u, which is 1, into integral of v dx whole dx equal to minus pi square by n minus 1 power n plus 2 by n. Sin of n pi is 0, sin of 0 is 0, so this first term goes to 0. The only term we have remaining is integral of sin nx will be minus cos, so we have already a negative sign outside, so cos nx by n square evaluated between 0 and pi. This will come out to be minus pi square by n minus 1 power n plus 2 by n cube cos of n pi minus 1, so minus 1 power n cos of 0, which is 1. This is I2, and our original computation was Pn sin hyperbolic of n pi 2 by pi I1 minus I2, 2 by pi I1 minus I2 n sine hyperbolic of n pi is equal to 2 by pi. I1 was minus pi square minus 1 power n. We have minus 1 power n into the case, so let us just treat it as minus pi square by n minus 1 power n minus pi square by n minus 1 power n minus I2. So plus pi square by n minus 1 power n minus 2 by n cube minus 1 power n minus 1 implies that bn sine hyperbolic n pi is equal to 4 by pi n cube into minus 1 power n minus 1, or bn equals 4 times minus 1 power n minus 1 by pi n cube sine hyperbolic of n pi. That was a lot of work to compute the value of bn. Now we can substitute it into our general solution for the equation. So the solution was f of x into y of y, which, what did it come out to be? Bn sine nx sine hyperbolic ny summation from 0 to infinity bn sine nx sine hyperbolic ny, which turns out to be bn is 4 minus 1 power n minus 1 by pi n cube sine hyperbolic n pi times sine nx sine hyperbolic ny. Now let us look at this term here. What happens when n is even? N is even, then minus 1 power n will equal 1. Therefore, minus 1 power n minus 1 shall equal 0, or the entire series will go to 0. Thus, we can further simplify it to say that the solution is only the odd terms of the series. So the solution is u of xy equals n is odd for minus 1 power n minus 1 by pi n cube sine hyperbolic of n pi sine nx sine hyperbolic ny, and when n is odd, minus 1 power n equals minus 1. So this can even be further simplified to minus 8, or oh, I think this is unnecessary, so let us leave it at this. This is the solution. Did I invert some sign here? I'm just checking with the standard solution. Bn, so this was this. This had to okay. So this is where the problem lies. Here we had a negative. So a negative will come here. This will mean that the terms will okay, okay. Or so in fact it should be 4 times 1 minus 1 power n by pi n cube sine hyperbolic n pi sine nx sine hyperbolic ny. This is the complete solution for the given boundary conditions of the Laplace equation. Now, solving PDEs involves a lot of, say, rigorous and laborious calculations, and it is easy to commit mistakes, such as the one I just committed. So, please be patient and careful when you are solving such problems. Also, if you notice that I am making some mistake, please feel free to point it out. Let me just make a note here that this has been solution has been continued at the end. Um, Slide number 40. Let us look at another Laplace equation. This time, however, we also have some conceptual questions in addition to the overall solution of the PD. So maybe I'll leave the solution of the PD as an exercise. I already solved the previous one in exquisite detail, but let us look at the conceptual parts. So we are given a Laplace equation again on a square region D of edge length pi, and the boundary conditions are u of 0. Let us sketch it. That might help. So say this is the xy plane. This is the region D. It's a square region of length pi of each edge. You have the value of function u at 0, comma y is 1. So on this entire edge, we have u equals 1. U at pi comma y is 0. So on this edge, we have u equals 0. U equals at x comma 0 is 0 as well. And u at x comma pi is unknown at this moment. This right here is the region T. The first question is, what should be the value of u, or what should be the boundary condition prescribed on u x comma pi so that u at pi by 2 comma pi by 2 is equal to 2. So u pi by 2 comma pi by 2 will I say at the center of this section. So this is the point pi by 2 comma pi by 2. So what should be the value of the boundary condition such that this is satisfied? Now, as I described, the one of the interpretations of the Laplace equation is that it is the steady state heat equation. And when we are talking about the steady states, the transient part is always already zero. So the value of the function at the centroid will simply be the line average of the boundaries. So at each boundary, the value is say 1. We are also multiplying it by the weight, which is pi in this case, to take the line average. Had it been some L comma K, we would have multiplied it the x boundaries by L and y by K and so on. Here the weight of each, the length of each edge is pi itself. So the weighted mean will be pi of 0 plus pi times. Say I have at this boundary, let it be A. And by the sum of the weights, again, so I'll just write the general formula here just in case. So had it been the x edge would be so ln k, then we would have written k times say 1 plus L times 0 plus k times 0 plus L times A by k plus L plus L. And this comes out to be pi 1 plus A by 4 pi equal to 1 plus A by 4. But the value at this interval is already given to us, it is equal to 2. 1 plus A by 4 is equal to 2, so 1 plus A is 8 or A is 7. Therefore, the boundary condition at u equals pi 0 comma pi or x comma pi should actually equal 7 for the value at the centroid to be equal to 2. Now, once again, this comes purely from the fact that the uh, solution of the Laplace equation may be thought of to represent the steady state heat equation. And in the steady state, because of the absence of any transients, the solution at the centroid will simply be the line average or the weighted average of the four boundaries. The second question was, is an initial condition required to solve uh, whatever we just did? And turns out no, it was not needed, and that is because So an initial condition is not needed. Initial conditions are needed when there is a time dependency. The Laplace equation represents the steady state solution, as we have been saying, and there is no time dependency. Now, the third question is actually asking us to solve the given PDEs. And we see that once we have determined the boundary condition for the top boundary as well, this will become something like we have u equals 1, u equals 0, u equals 0, and u equals 7. So here we see that the boundary data is non-zero on two edges. But remember that I had put in a comment saying that the Laplace equation is solvable by separation of variables only when any one of the boundary data is non-zero. The rest have to be zero. So how do we go about solving this problem? So let's take a short break. Meanwhile, you can think how we can approach this problem, and when we return, we can discuss it. So let us resume. The problem that was in front of us was how to solve Laplace equation when the boundary data is non-zero on more than one boundary. Because we saw that how it is solvable by separation of variables only when one of the boundary data is non-zero. The rest must compulsorily be zero. And the way to do this is, of course, tried and tested superposition. So the way we do this is we decompose the problem into multiple subproblems such that each one of them is solvable in their own right. Then we superimpose the solutions together. So here what we face is something like this. So we have u equals 1, u equals 0, u equals 0, and u equals 7. And we can break this into maybe even use a different color. So we have only one boundary condition non-zero, which is the left boundary in this case. We solve it. We already know how to do it. Plus a second problem where we now set this boundary to zero and only have the boundary data at the top boundary non-zero. Again, because only one edge is non-zero, we can find the solution. We already saw how to do it. And then we superimpose solutions of the two. So say we have solution 1, we have solution 2, and we superimpose them. That is, we have a linear combination of the two to obtain a solution to the entire problem. And I leave that to you as an exercise. It's simply pretty straightforward. And if you want, I can also share the standard solution at a later date, just so that you can verify yours. Now, another class of problems that was touched during the lectures was the Neumann problem. And here we have the formal definition of the same. So the Neumann problem in a plane consists of finding a function that is again harmonic on a given region D, as well as whose normal derivative assumes given origin the boundary C of D. So previously we had the function itself assuming some values. This time we have the normal derivatives of the function. Thus it can be formulated as del square u of xy equals 0 on D, such that del u del n is equal to g of xy for some xy in C. C refers to the boundary and gxy is a given function defined on the boundary of C. Another important result which actually deals with the existence of solution is this condition right here. and which says that the closed integral over the contour C of del u del n ds, which equals the closed integral over the contour C g ds, has to be necessarily equal to 0 for a solution of the Neumann problem to exist. And it's also formally stated here that the vanishing of the integral of the given normal derivative over the boundary of the region is a necessary condition for the Neumann problem to have a solution. If the integral of g over the boundary C of the region is not 0, the Neumann problem has no solution. Thus, whenever we are posed with a Neumann problem, the first step should indeed be to check whether the problem has any solution at all or not. And it can also be extended to the case that D is not a bounded region and C is not a closed curve, such that when we are dealing with half planes, maybe the right quarter plane, x greater than or equal to 0, q greater than or equal to 0, and the region is unbounded in this case, and its boundary curves consist only of the non-negative x and y axes. However, this result still stands true. We also have an illustrative problem where we are asked to check whether the Neumann problem has a solution or not. So del square u is equal to 0 for 0 less than x less than 1 and 0 less than y less than 1. So, and the boundary conditions for the normal slopes of the function given to us are del u del n is 0 on the left, top, and lower sides. So I'll just sketch this again. The boundary conditions given to us are del u del n is 0 on left, top, and lower. So, and del u del n is equal to y square on the right hand side of the square. And we are asked to check whether the given Neumann problem has a solution or not. So we already have the necessary condition. I'll just write it again. So the necessary condition for a Neumann problem to possess a solution is integral over the closed contour of the region D, GDS is equal to 0. And let us, here we can break down the given boundary into individual edges of the square region. So maybe the C1, first I need to mention which is which. So say this edge right here is C1, this is C2, C3 and C4. So to integrate along the entire boundary, I integrate it piecewise. So going over C1, C2, C3 and C4. Now let us evaluate the integral over these piecewise boundaries. So when integrating over C1, what is the value that the function takes? So here del u del n is equal to g is equal to 0. Therefore, the integral over C1 GDS is also 0, which is good because The value of the integral over the entire boundary should be 0. One of the parts is already 0. Let us integrate over the second piece. So here the value of the function is non-zero. It's equal to y square. Now let us see what are in for the boundary C2. X is equal to 1 and y goes between 0 and 1. So the value of ds is actually equal to, so ds is equal to dx I hat plus dy j hat. It is a small boundary element. So this will be x is equal to 1, so dx is 0. Uh, dy will have some value, and this makes sense because when we are going over this boundary right here, the direction along which we are integrating is along the j hat direction. So any direction vector which will point us along the contour will be pointed along j hat and will have a magnitude of dy. So let us find the integral. This is going dy is going from 0 to 1. Function g is y square and the magnitude of ds is say the norm of the ds vector, nothing but dy itself. Dy y square is y cube by 3. A definite integral between 0 and 1. So this will be 1/3. We found that integral over C2 GDS is 1/3. Let us go over the other contours. So here again the value of the function was 0. So integrating will give us 0 still. And for the fourth piecewise boundary, therefore integral over the entire closed boundary of GDS, which we decompose into the sum of GDS over the piecewise boundaries, is equal to 0 plus 1/3 plus 0 plus 0, which is equal to 1/3. But as we just saw, for the normal problem, to have a solution, this integral must have been 0. So integral over the contour del u del n ds g dx has to be 0, which is not the case here. There's The given Neumann problem does not possess a solution. Pretty intensive today, and we have also reached almost the end of our session. So there was one more question which I wanted to solve, but I guess we won't have time. So Anirudh, why don't you attempt it on your own? And maybe I can pass on the standard solution to you, and you can verify whether it works for you or not.
Yeah, sure. Thank you, Sourav.
Thanks, Anirudh.
Yeah.
So thanks for tuning in to week 5 of the live sessions of Computational Science and Engineering. I look forward to seeing you next week. There might be some notification regarding shifting of the live sessions. If so, any such information will be conveyed by the NPTEL team. Yeah, I look forward to seeing you again. Thank you.
Thank you. Bye.